Let's continue hacking some Solidity smart contracts. This is Ethernaut level 1, Fallback. In this video series, we solve all the Ethernaut challenges, which are Solidity-based smart contract challenges, where we have to perform some action, where we have to hack into them in some way or another. If you're entirely new to Web3 blockchain Solidity, then be sure to check out the first video in this series where we kind of introduce how these challenges will work and what we have to do. But if you've already done that, then keep on watching this video because right now we are going to solve challenge number 1, Fallback. As always, we get a contract and a goal to achieve. In this case, the goal is that we need to claim ownership of this specific contract and we need to reduce its balance to 0. So pretty much just drain all the funds from it. Now let's take a look at the code for this contract. As always, it starts off with defining the version of Solidity that should be used here, which is in this case a version 0.8, which is at the time of making this the newest version. Now we define a contract. The contract's name is Fallback. And in this contract, we define some properties. These properties kind of define fields in our contract. The first one is a mapping from address to unsigned integer. A mapping can be seen as a dictionary in other languages. It says, hey, this address has this amount of uint. This mapping is public and the name of it is contributions. Next up, we have a public address named owner. Following that, we start with a constructor. A constructor is called whenever a contract is deployed. In this constructor, we set the property owner to be equal to the message.sender. For a constructor, the message.sender is the person who deployed the contract. So in this case, we just set the owner to the deployer of this contract. Next up, we also set a contribution for this owner, for the message.sender, and we set the contributions for him to be equal to 1,000 times 1 ether, which is 1,000 ether. So a very, very large amount that this owner has contributed according to the contract. So that is the constructor. That is what happens when this contract gets deployed. Next up, we have a modifier only owner. Now, modifiers are kind of defining code that can be ran before or after a function calls. So for every function, we can say, hey, use this modifier, and then this code will be called before or after that function. So in this case here, we see that it starts out with a require statement, and it requires that the message.sender, so the person making this call to a function, is equal to the owner. If that's not the case, the function is not going to execute and it's going to error out saying that the caller is not the owner. But if the caller is the owner, then we will reach this underscore, and this underscore just means, hey, call the function that this modifier was applied to. We could even have code after this underscore, which is then code that will be executed after the function executed. So this only owner modifier will just ensure that any function that is applied to this modifier will only be able to be executed by the owner of this contract. Following that, we have the contribute function, which is public, meaning that it's, well, public. Any other contract can call this, we can call this, but also from inside the contract it will be callable. But it's also payable, and that's something new. A payable function means that we can send some amount of funds with our call to this function. So we can say, hey, I want to call the contribute function with 1 ether, for example. And in this function, well, it's just a normal function. It starts with a require statement saying that the message.value, which is the amount of funds that we send across with this call to the function, that amount has to be smaller than 0.001 ether. So the amount that we sent has to be fairly small. If our amount that we sent is bigger, the function will revert and not execute, which also means that you will get your funds back. If you are sending a small amount, then it will change the contributions property and it will set your contribution. It will just add the amount that you sent to your contribution, right? So that is all fairly clear. However, now there's an interesting if statement. If after adding your contribution, you have contributed more than the owner has contributed, then you become the owner. This is very interesting because the goal of this challenge was for you to become the owner and drain all its funds. This could be a way for you to become the owner. However, you're only allowed to send very small amounts of Ether to this contract. And that's a bummer because the owner has 1,000 Ether contributed. That's what was set in the constructor. Of course, the owner hasn't actually sent 1,000 Ether into this contract, but that's what the contributions mapping says. So, well, you will need to send 1,000 Ether for you to become the owner. You can only send that in amounts smaller than 0.001 Ether, which means that you would have to send 1 million. You would have to make this call 1 million times. This is, well, a bit difficult, not that easy to do. It will, well, take a really long time, I suppose, and cost a lot of money. So maybe this is not the best way of becoming the owner. So let's just continue reading and see what else is going on here. Because we have another function here, the get contribution function, which is public, but it's also a view function. This means that it doesn't make any state changes to the contract, and also means that we can call this without causing a transaction. As we saw in the last video, if we make a transaction, it needs to get mined on the network, which takes some time, which costs gas. View functions don't need that because they only retrieve values, they don't make changes. Hence why this function can be called really quickly, and we'll obviously discover that a bit later. This function also returns something, an unsigned integer. And if we see what it returns just returns the contributions of the message sender. So this is just a nice helper function for us to be able to see our contributions. Following that, we also have a withdraw function. This is again a public function, but it has the only owner modifier applied to it, which means that only the owner can execute it, if you remember from earlier where we looked into the definition for that modifier. Now, what does the withdraw function do? Well, it takes the owner property and it turns it into a payable address. Now, the owner is already an address. This payable wrapper is just going to make it a payable address, which after this contract has been compiled doesn't really change anything, but it's just something Solidity added to make sure that developers know explicitly, hey, this thing is a payable address or an address. You shouldn't really be concerned with it too much. It's just going to turn that address into a payable address because it then wants to transfer funds to it. The transfer function takes the amount that needs to be transferred. In this case, how much are we transferring to the owner? Well, we're taking the address of the contract, and we're taking the full balance. So the full balance of this contract will be transferred to the owner if that withdraw function is called. So our goal was to drain the contract from all its funds to get all the funds. If we become the owner, then that is trivial because then we can just call this withdraw function and, well, easy peasy, we have then withdraw all the funds from the contract. Lastly, we have one more function, and this is kind of a different one because this one doesn't use the function keyword. It just says receive with no arguments. It is external and payable. So payable, we know what that means. We can send money to the contract while making this call. And external is very similar to public, only that external means that it cannot be called from inside this contract, so only external sources can call this function. That is done for gas optimization because of the way it handles arguments. I'm not too big into all that, but it just means that we can call this. However, why does it not have that function keyword before it? Well, that's because receive is a fallback function. It is a function that we cannot explicitly call. However, this function is executed whenever we send money to this contract without explicitly calling another function. So if we just make a transaction to this contract with some Ether, then this function will be called. However, obviously, if we make a transaction to this contract by calling, for example, the deposit function or the contribute function with some funds, then the contribute function will be called instead. So the receive function is a fallback function. If nothing else applies, then that function will be called. That's kind of the way you should see it. So, okay, What does that function allow us to do? Well, it first of all has a require statement. It requires that the message.value is bigger than 0. So we need to send some funds to this function. And our contributions, the contributions of the message.sender, our contributions need to be bigger than 0. So we need to have contributed something to this contract. But if those are the case, then we become the owner. So this is very interesting because these checks here, I mean, we have to send some funds in this receive function. That should be fairly easy. And we have to have contributed something. That should also be fairly easy. And if that's the case, then we become the owner. So now we have a clear goal of what we need to do. We need to first contribute something to this contract and then call that receive function. And then we become the owner and we have solved the challenge because then we can just withdraw all the funds. So let's start playing around with that. And in order to play around with this, I'm going to copy all the code from here and I'm going to go into Remix. Remix is an Ethereum IDE, so a development environment that makes it really easy to interact with contracts. And the reason we're doing that is because it allows us to use a VM, a virtual machine, that has a blockchain on it that we can work with. And that means that we're not dealing with an actual blockchain or a testing blockchain, because those are very slow, right? In the last videos, we saw that if we want to make a transaction, it takes up to 20 seconds to have that transaction being mined. That takes a long time. So for testing purposes, we first want to test in a virtual machine where we control everything, where things happen almost instantly. And then later we can take it into a real or a testing network so that we can actually execute our actions. So for now, we are in the Remix IDE. This is just in your browser as well. So you can just Google Remix Ethereum IDE and you will find this. Here in the File Explorer, we can create a new file. I have made a Fallback folder here, and I can create a new file, which I will call fallback.sol. Then I will just paste all the code in here. Of course, if you paste code, it's going to say, hey, watch out with that stuff, because obviously if we start interacting with this or deploying it on the mainnet, that can cost us money and can cause some bad things to happen. We don't have to worry about that for now because we're only going to be working in virtual machines where all the funds that we have are kind of fake, right? So we have all our code in here. Now we can go into the Solidity compiler here on the side, and now we can compile this. We will see that that just works. We can also compile by just pressing Ctrl S. So let's quickly make an error here. Now if we compile, we see that there is an error. We can fix that, and then with Ctrl S, compile again. And now the contract is valid again and it compiles. So okay, that is our contract compiled. Now we can really easily interact with it by going to the deploy and run transactions window. Here we see that there are a couple of settings. For example, the environment. So right now I'm on the Remix VM in London. But we can also switch to the injected provider MetaMask, and that way we can actually interact with things on the test network or on the mainnet. But we want to stick with this VM because that's going to allow us to really quickly do things. So let's stick with this VM. We see that now in the account section, we have just a bunch of accounts that have 100 Ether in them, just testing accounts that we can use, which is really nice, of course, for us to play around with. We then see we can set a gas limit. We shouldn't be worried about that for now. We can also set a value. Then at the bottom, we have our compiled contracts here. So right now, there's only this one compiled contract and a big deploy button. At the bottom, we will see our deployed contracts. So let's quickly just deploy this contract. Now at the bottom here, we see that it has been added to our deployed contracts, and we can look into it. So looking into it and scrolling down, we see it's a fallback contract. It has a balance of 0. We can get the owner for this contract. So click the owner button and then it sees, okay, now this is the owner. The contributions of this person is, well, 1,000 Ether. As we saw in the constructor, the owner has 1,000 Ether of contributions. And that's kind of how this contract works. We can see the contribute function. It is a red button here. That's because it is a payable function. Payable functions will be red. The withdraw function is a transaction that is not payable. So performing a withdraw makes state changes and therefore has to be mined. So it is an orange button, and then the blue buttons are just getting view functions or properties that are public, and we can just interact with them without having to make a full transaction. So right now we are the owner of this contract. And let's quickly contribute something to the contract so that we can also see how that works. So to contribute something, we change the value here to a certain amount. Notice that the value here is currently in Way and not Ether. Now, what is Way, you may wonder? Well, one Ether is a lot of money on the mainnet, right? And so oftentimes you would have to be working with 0.001 Ether or even lower amounts, and that can get kind of tedious. So Way is kind of a smaller denomination of Ether. So there's this nice converter here, so simple unit converter, where you can see that 1 Ether is a lot of Way. And that makes it easy, because if we want to deal with small amounts, you don't always want to type 0.000001 Ether, you just want to type 1 Way or Gwei. So in this case, let's have our owner contributes like a sizable amount of Way into this contract. So whatever that amount is, let's contribute that to the contract. That works, and now we can see that the balance is this amount of ETH. Our contribution has gone up a little bit. Okay, now let's change to a different account. Let's just take this account. This one obviously can now not do a withdrawal. As you can see in this debug window here, it reverts because this account is not the owner. The owner is 5B38 and we are BD8. So we cannot do that. However, we can do other things. We can, for example, get our own contributions, which is 0 right now. But we can also contribute to this contract. Now our goal is to call that receive function, and in the receive function, if you look at it, we see that we have to have a contribution higher than 0. So let's first make sure that that is met. So let's just send 1 Way into this contract. So I'm going to contribute 1 Way. That succeeds, and we see that 1 Way has been added to this contract, and the balance is now this number. Our own contributions now are 1. That's perfect. So this is met. Sorry, now we just need to call the receive function on this contract, but we see that there is no button for the receive function. And that is because this receive function is a fallback function, meaning that it will be executed when we send some funds, when we transact with this contract and send some funds to it, but we don't explicitly call any of these functions. In our Remix IDE, we can do that with these low-level interactions by just transacting with the contract. But first, obviously, we want to send some value. So let's send 1 Way, and then let's transact. That will succeed. Now the contract has 50002 ETH in it. So our money was sent. But now if I make this call to the owner, we see that the owner is now us. We are now the owner. We have become the owner of this contract. As you can see, our account is BD8 and the owner is BD. We are actually DD8 apparently. I read that wrong all this time, but we are DD8 and the owner is also DD8. Okay, so we are the owner. Okay, our contribution is still just 1. However, the contribution of the actual owner is quite a bit larger. But now that we are the owner, we have solved this challenge. We just need to withdraw all the money, which we can just do by the click of a button. The balance here is now 0 ETH, and our account now has 100 dots and some more ETH than it had at the beginning. So that means we've solved this challenge. And that's quite cool. Obviously, we just did all of that in the VM here to play around with it, but we can now go ahead and do that on the actual Ethernaut test network or with the actual contract that is deployed here. So the first thing that I'm going to do is I'm going to get a new instance here, which is obviously going to pop up MetaMask. Now I'm going to have to make that transaction to get a new instance. I will then also go into the inspector tools because this is where we will be doing all the hard work. And in the console, we can now see that it has sent this transaction and it's getting us an instance. All right, we now have an instance. Let's quickly just clear all of this. So we can now do like an await contract dot owner just to see who the current owner is. You can also see who the player is, that's us. So as you can see, the player and the owner are different. So the first step that we need to do is we need to contribute something to this contract. So let's first of all check what our current contributions are. So contract.getContribution. What is that? If we open this up, we see 0. We have currently contributed nothing to this contract. So that needs to change. Well, let's do that. Let's do a contract dot and then contribute. And we need to send this, but this is a payable function. We need to send some value with it. And we can do that by applying a parameter here with a dictionary that or an object that has the value key set to the value that we want to send. And in this case, I just want to send one way because we just need to send a little bit. So I can do that. Now we see that MetaMask pops up. We need to confirm this transaction. The transaction has been sent, and I'll see you back when it has been mined. So now our transaction has just been mined, and now we can see if that went through, right? I mean, it went through correctly, but we can get our contribution once again. And now we see that we have contributed one way to this contract. So we have a contribution. And that a contribution was important because now we want to call that receive function. Before we call that receive function, let's again double check that we are not the owner. So await contract.owner is this, and we are the player, which is not the owner. Okay, now we have to call that receive function. Can we do that by just doing contract.receive? No, that doesn't exist. We need to send a transaction to this contract, and we can do that with send transaction. So send transaction is going to allow us to create a transaction. Now our transaction, again, is going to have some funds, because in order to call this receive function, we need to send some funds. So let's just, again, add an object here with a key, value, and then the amount of weight that we want to send. In this case, 1. So let's make that transaction. Okay, so again, MetaMask is going to pop up. We confirm the transaction right here. It has sent the transaction, and I'll see you again when it has been mined. And the transaction has just been mined, which is great. Now let's double check that we have become the owner, because if all went well, then in our receive function, the message.value was higher than 0. The contributions of our sender were higher than 0. So normally we should be the owner now. And if we call await contract.owner, we see that now the owner is equal to the player. So we are the owner of this contract. So all that's left to do for us now is to actually withdraw all the funds from this contract. And that's really easy because there's just a withdraw function that will do just that. So let's just call this withdraw function. MetaMask is again going to pop up. We are going to confirm. The transaction is going to be sent. And now we wait once again. And after that transaction has been mined, then we should be able to see as well that the balance of the contract is now 0. So we can use the getBalanceHelper function by the Ethernaut game here of the contract. That did not work. Let's try that again. So let me quickly clear the window here so you guys can see. Clear the window. And I think we have to do contract.address. So get the balance of the contract, which is 0 right now. So this all worked. We withdrew all the money. And I think we can even go and check that out on Etherscan. So in the last video, we also covered Etherscan really quickly, and we showed that Etherscan is kind of a block explorer, a blockchain explorer. So here we can see our call to withdraw. We can see it. We can go and view it on the block explorer. And here we can see our everything going on here. We can see our transaction here. We have the hash of it, its status, it has succeeded, the block it was in, when it was mined 53 seconds ago, from this contract to this contract, and it transferred two-way, which is what we also sent into the contract. So we drained all the funds from our instance contract to ourselves. And this can obviously all be seen on Etherscan because everything in the blockchain is public and you can see everything going on. But that has been this challenge. All that's left to do for us now is to submit the instance here, which again we have to accept. But once we've done that, we have solved this challenge. And if we've solved this challenge, Ethernaut would also say that we know the basic of how ethers goes in and out of contracts, including the usage of the fallback method. So we have learned about the fallback method here. We've looked at some more contracts, so we're continuing with gaining new skills that will be really helpful if we want to pursue a career in smart contract bug bounty or smart contract auditing in general. If you like this video, then leave a like down below. If you have any questions for me, anything that you want more clearance on, anything that you want more information on, let me know down in the comments and I will be happy to help you out. But for now, this has been it for this video. Next week, we will have the next challenge in the series. And if you want to make sure that this whole series will get finished, then be sure to leave a like, because that really helps us and proves to us that we need to make more of these videos. But that has been it for me. I'm Pink Draconian, and I'll see you next week in another video. Take care, guys.